In this video, I'm going to talk about how we can have finer control over reading and writing text files. We saw in the previous video that there's just a simple little method that can take the name of a file and then return you all the text in that file. We might want to do more complicated and sophisticated things with files than that. I'm going to talk about what are the special considerations for handling unmanaged resources. And by unmanaged resources, I mean things like files, things that the operating system manages for you that the C# runtime does not manage for you. And there are, in particular, some complicated scenarios involving the intersection of unmanaged resources with the exogenous exceptions that are associated with things like files that can make it quite tricky to figure out what the right code to write is. And we're going to talk about some features of C# that allow you to write this tricky code more concisely. So let's just get right into some code here. But once again, I've created a little console application. Now, for pedagogic reasons, throughout much of this code, I am not going to be handling some of the exogenous exceptions that you would want to handle. Right? There are control flows that I want to illustrate here that are already a little complicated. They would be made even more complicated if I try to handle all of the file not found exceptions and all of that kind of thing. So we'll try to follow along. We'll try to keep it simplified for now, and then we'll see what the real code would look like a little later. So we never did actually open that text file before, right? We kept on trying to open a file that didn't exist, and we never succeeded. So this time, let me show you how to produce a text file. We're going to write one out, and then that we know that it's there, we'll read it back in. So let's just step into this code and see what happens. So the first thing I'm going to do is I'm going to get a string that is the path to the My Documents folder on my machine for me, for the user that is currently active. So there's a method, getFolderPath. It's a static method on environment. It takes an enumerated type called special folder. I mentioned in the video about enums that it is legal, although rare, to put an enum inside a class. And in this case, they have put the special folder enum inside the environment class. And so, of course, the way you use the enum is you say environment.specialfolder.mydocuments. And then there's a whole series of special folder enums that are in here that you can pass to the getFolderPath method, and it returns you the appropriate path. All right, so once we have the appropriate path, I'm going to call path.combine, another very handy static method that takes a path and a file name, and it puts them together for you. And so there we go. There we have the path to the file that I want to create. And now I'm going to call this handy little helper method writeAllText. It takes two arguments. The first argument is the path to a file, and the second is the text that you want to write into it. And sure enough, we have written this file out to disk. If I opened up my Documents folder, we could take a look at it. In fact, why don't we just do that? All right, so there it is, my file.txt. And if we open that up in Notepad, it says hello world. All right. We can now use the readAllText method that we kept on trying to use unsuccessfully in the previous video and find that, sure enough, we just read all that text back in. We could then say, you know what, I want to replace that file with a different file. And here, we're going to use a version of this method. Instead of writeAllText, this one's called writeAllLines, and it takes an array of strings, and again, writes it out to the file. So if I take a look at the file, now it's got all of that text in it. The previous file is gone. All right, so this is useful for tiny little files that are 1 or 10 or 100 or 1,000 lines. But suppose the file had 100,000 lines in it, or 200,000 lines, or 1,000,000 lines in it. Right? It seems like we might not want to read the whole thing in at once. We might want to read it in, say, a line at a time and do some processing as we go. The file might be too big to fit into memory, for that matter. In C# we have a thing called a stream that is very useful for these kinds of scenarios. A stream it's an abstraction. Remember, when programming, we're always talking about abstractions. And it allows us to programmatically manipulate a stream of bytes. So a byte, a byte, a byte, a byte, a byte, a byte. Millions or billions or tens or however many of them, some finite number of bytes. Okay. Streams are usually associated with some kind of file I/O or network I/O or something like that. They don't have to be. There is a type in the .NET runtime called memory stream, which is essentially, I would like to treat this array as though it were a stream of bytes. Mostly used for testing code, where you want to test whether your stream handling code is correct without actually having to go out to the internet in your test cases. But yeah, usually streams are file or network I/O. And since bytes are not a very pleasant thing to work with, there are stream readers and writers. And they are an abstraction that sits on top of streams and say, I'm going to manage this stream of bytes, and I'm going to figure out what kind of text is in it, and I'm going to talk to you using strings like you would rather me talk to you, so that you don't have to deal with the bytes and the byte encodings and figure out, is this in Unicode or ASCII or all of that. Right? The stream readers and writers take care of that stuff for you. All right. So how would we use a stream reader? I'm going to create a block here, just because I'm going to be reusing some of these variable names throughout this program. I'm going to create a new stream reader. I'm going to give it a file name. So now I have my reader here, system.io.streamreader. And I'm going to go into a while loop. I'm going to say, while we are not at the end of the stream, and so the stream is producing a continuous stream of text coming at us, and we're going to be reading it and reading it and reading it and reading it until the end. So while we're not at the end, read a line, and then write the line out to the console. And so the first line read in is alpha, and then the next line read in is bravo, and so on. And we keep on doing this until the reader is exhausted. It's at the end of the stream. We break out of the loop. All right. So we've read through to the end of our stream. Are we done? Can our program just keep on going? As it's shown here, this code is wrong. You are required to close a stream when you're done with it, because otherwise the stream stays open indefinitely. You can imagine a situation where you have opened a file, you've read a bunch of text out of it, right? Then you're done. You don't close it, and your program keeps on running. And then some other program some other process on the machine says, well, I would like to read that file now. And the operating system says, well, I'm sorry, you can't, because somebody else is using it. Well, this code is done using it. It's read through to the end of the stream. But the operating system doesn't know that. Right? For all it knows, the reader is going to say, oh, reset to the beginning and read it again. So you are required to close streams when you're done. And you can call reader.close, or you can call reader.dispose. They do the same thing. So this is true for stream readers. It's also true for streams, for stream writers, the whole bit. All right. So now let's start thinking about the exogenous exception problem. Right? Suppose we open the stream, right? And then we are reading. We don't get to the end of the stream. But let's suppose the file is on a network share, and somebody unplugs the network while we are reading this thing. Right? So suddenly, there's going to be a failure. The failure is going to be surfaced as an exception. The read line could throw an exception. We still are required to close the reader. Right? So this seems like maybe we're going to have to write some exception handling code to take care of this. Right? So let's take a look at how we might do that. I'm going to stop this code here. All right, so suppose that we create a new reader. Right? Then we have a try block. Then we have the code here that reads one line at a time, one line at a time, one line at a time. This throws. Control is transferred to the catch. We handle the exception. And we close the reader. Is that right? What I just said sounds like it's right. But there's a problem. That works if the thing that throws is the read line, right? But suppose the thing that throws is the new stream reader. right? This guy could still throw, right? There could be an exogenous exception here because the file name could be wrong. It could be to a file that doesn't exist or is locked or whatever, right? So we haven't handled the case where this thing possibly throws. All right, well, we can't close it if it threw while we were trying to open it, right? So what are we going to do? Well, let's try this. We'll make a block here. We'll try. We will now open the reader inside the try. We will read every line out of the file. So if either of these things throw, if the stream reader construction throws or the read line throws, then control transfers to the catch block. We handle the exception appropriately. So the exception is gone. It's gone away. And then we close the reader. Well, we can't do this because this says the name reader does not exist in the current context. Reader was declared inside the block of the try. And remember, local variables are scoped to the block that they were declared in. This is outside that block. All right, so that's not going to work. So let's try this. Let's create a variable called reader outside of the try block. We'll set it to null. Then we will create the stream reader inside the try block, read all of the text inside the try block. OK, now if any of these things throw, then control is transferred to the catch. The catch eats the exception. It's fine. Everything's good. And then we say, if the reader is not null, then close it. And of course, in C#6, we could use the question mark dot operator that I talked about in a previous episode, right? We could just say reader question mark dot close. And if reader were null, then it would ignore the dot close. And if reader were not null, then it would call it. That's a use of the Elvis operator that I didn't mention in the previous video where I talked about that. All right, so is this right? This code actually is right. This is good. But you remember the scenario from the previous video where we were trying to catch something just for the purposes of logging. And we wanted to do some logging and then rethrow the exception to an enclosing try-catch. How's that going to work? All right, so we're going to have try. We're going to call some method that does some file thing. And then we're going to have the catch here. And this is the catch block that we actually intend to handle the exception. Right? Well, let's take a look at what do file thing does here. All right. So I've just taken the code that we just had and put it into this method here. So we've got a reader. It's a local variable. It's outside the try block. So it's scoped to the whole body of do file thing. We're going to set it equal to null. We create the new stream reader. We read through all of the lines. If something goes wrong, then we catch the exception. Now we need to close the reader. So we check to see if the reader is not null. Then if it's not, then we close it. And then we rethrow it. All right, so let's think about what happens here. Suppose something in here goes wrong. Control is transferred to the catch block. We close the reader. We throw. Control is transferred to our caller. And it handles the actual exception. That's fine. Suppose nothing goes wrong, which remember is the likely case. Exceptions are called exceptions because they are exceptional. In the success case, the likely case, we enter the try block. We create a new reader. We read through to the end of the stream. The catch block is never called, right, because no exception happened. So control falls off the end of the try. And now we need to close the reader, right, because we opened it. We need to close it. Now, there's no need to check for null here, because if we got this far, then we know that the creation of the reader succeeded. So that's OK. But does it strike you as odd that we had to write the close code twice in this case? This seems like it is error-prone, and it seems like it's confusing to have the same code in two places like this. All right, it seems like it's error-prone and inelegant to have to remember to write that code twice. What we need is a different kind of handler than a catch handler. What we really need is we need something that runs whether there was an exception or not, right? Because we want to close the reader regardless of whether there was an exception. That's why we had to write it twice, once in the exceptional case and once in the normal case. So we're going to rewrite doFileThing to use a different kind of exception handler called a finally handler. So here's how that works. So what we're going to do here is we are going to move the logic that closes the reader out of a catch block and into a new block called a finally block. And so I'm going to take this out of here, move that in here. Right? And then we would have in here the logging code would go there. We would then rethrow the exception. And then the finally block actually does the close. All right, so now let's think about what the control flow is here. We create the reader variable. We assign it null. We enter the try block. We create a new stream reader, and we try to read some lines out of it. If something in there fails, then the exception is caught. We write code here to log the exception. We rethrow it. As control leaves the try via the rethrow, the finally block executes. The finally block is the thing that happens eventually, right? That's why it's called finally. The last thing that we do before we leave is we check to see if the reader is not null. If it's not null, then we close it. Then control transfers to the outer catch block that actually handles the exception. So this is the sort of standard way to do this, is to have a try, a catch, and a finally. So the syntax of the try, catch, finally block goes like this. So you have a try, and then a block that contains some statements. Then you have 0 or more catch handlers. And then you have a finally. The finally also has a block followed by some statements. If there is a finally, then the catches are optional. You can omit all of the catches. Right? If there is no finally, then you have to have at least one catch. Right? You can't just have try with no handler at all. There has to be either a finally, a catch, or both. And there can be any number of catches. So to summarize how exceptional control flow works, because you may be a little bit confused at this point because it's complicated. When an exception is thrown, the runtime searches for an enclosing try block, right, that has a matching catch. It can execute exception filters as it goes while it's trying to find a matching catch. The enclosing try that has the appropriate catch handler might be in the caller. Right? If it can't find a suitable catch block, then the program is going to crash. Something terrible is going to happen. And what exactly happens, whether it says, would you like to start a debugger, or reports it to Microsoft, that's up to the operating system to decide. Supposing that a suitable catch block is found and that the program is not going to crash, then the finally handlers are executed as control leaves each try. As control leaves the try, regardless of whether control left it via the exception or left it normally. Right? So the finally blocks execute sort of from inside to outside as we go up the call stack. Finally, control passes to the catch. And then if control leaves the catch, either normally or via another exception, and there's a finally, then the finally happens last. All right, that may have been more confusing than it was clarifying. So let me actually illustrate with a totally contrived example. All right, so here I'm going to try once again to open a bogus file. And I have a try block that calls some method that's going to try to do something. I have a catch block with a filter. The filter checks to see is the file that was not found equal to the file that we passed in. And then finally, there's going to be some code in here that I want to run when things are done with this try. Right? So let's just trace through all this logic and see what happens. So we call do another file thing. This guy tries to create a stream reader for this file. That fails. Control passes immediately to the filter. So now the filter returns true. So now we know which catch block is going to run. Before the catch block runs, now control has passed back into the do another file thing method. We're going to run the finally block. We run the finally block because control is leaving this try. right? Control is leaving this try because an exception was thrown, and we have a handler in an outer block. So the finally runs. We need to close the reader. Right? The reader was never non-null anyway, right? So there's nothing to close here. But if it were, if the read line had been the thing that failed, then we would have needed to close the reader. And now control transfers to the catch block. When control leaves the catch block, control transfers to the tries finally. This tries finally, which then does whatever it needs to do. Does all of this strike you as super confusing, right? Because it certainly strikes me as confusing, right? We have seen control has been bopping back and forth between multiple different methods, trying to figure out what's the catch block that handles this exception, when does the finally block need to run, all of that stuff. One of the reasons why this is confusing is because we are mixing up two things, right? Two fundamentally related but different concerns. The first one is, how do we handle the exogenous exceptional cases that we need to handle, right? And as I mentioned before, there are a bunch of them that we need to handle that I've omitted. And second, how do we ensure that the reader is closed, right? What we want to do is we want that thing to be closed when control leaves the method that created it, or the block of code that created it, regardless of how it left, regardless of whether it left via the exceptional case or via just the regular I'm done with this thing case. And anytime you end up mixing concerns like this, the code gets super complicated and it gets super hard to reason about. And so C# solves this problem by having a special control flow mechanism just to solve this second problem. How do we ensure that the reader is closed? So the right way to write all of this code that we've been doing all of this time, right, is like this. We have a try block, right? Then we have a using block in here. And we'll talk about what the using means in a minute. The using has a local variable declaration here. It says the reader is a new stream reader. Right? Then inside the block of the using, we actually attempt to read the lines out of the stream. Right? Then we have a catch block. The catch block has whatever exception handling is appropriate for the exogenous exceptions that can be thrown by this stream reader. And that's it. Right? We have no other fancy logic here that we need to worry about. The using block is the thing that takes care of, I am going to make sure that this reader is closed by the time that this block is exited. Right? That's its sole job, and it's very good at doing that. Right? And then this try catch is the thing responsible for dealing with the question of what if something in here failed, because these things can throw exogenous exceptions. So we've now hidden the cleanup logic. You'll notice there was no call to close in there. Right? The using block is responsible for ensuring that the dispose method, the close method, is called. So that only leaves the try catch block there for the exceptional cases. So we have a more clean sort of separation of concerns here. Now, a couple of times in the last few videos, I've used the expression syntactic sugar. And the using block is another example of a syntactic sugar. A syntactic sugar is a feature that the designers of the language have added that just makes it more concise, elegant, useful, easier to understand, usually by taking some code that is kind of long and complicated and intricate and saying, you know what, we're going to provide you a nice short way to write that code. Let the compiler worry about figuring out how to expand it into the longer, more intricate thing. So the using block is a syntactic sugar. The for each block is a syntactic sugar. There's a bunch of different syntactic sugars in C#. They're all there to just allow you to make your code shorter and easier to understand. So what is this using statement that we just used? It's a syntactic sugar, and its job is to ensure that streams and stream readers and anything else that creates a resource that needs to be closed explicitly so that somebody else can use it is actually disposed of without you having to write the code that calls close, without you having to write a try finally, without you having to write any of that stuff. Right? Now, it has nothing to do with the using directive. You remember at the top of every program we've seen, there's been like a using system directive. The using statement and the using directive have nothing whatsoever to do with each other. It's just kind of an accident of history that they're both called using. So the syntax for the using statement is just using, and then the type of the resource, or var, is legal in here. As you've seen, we used var, but we could have said stream reader. Then the name of a variable, an expression which initializes it. This is usually something like new stream reader. And then a body. So like the if and while and all of those others, the body can be any statement. It doesn't have to be a block. The using statement is a sugar for this try finally. So if you see this code, then what the compiler is actually going to compile is it's going to create a block. It's going to create a local variable of this type, initialize it, put the body into a try, and then make a finally that checks to see if the resource is null, and if the resource is not null, then to dispose it. And the standard in C# is that the standard in .NET is that there is an interface called idisposable that has a method called dispose. And we'll talk more about what that means to implement an interface in a later video. But just suffice to say, it is standard in C# for every object that needs to be disposed of in this manner by a using block implements a dispose method that does the right thing. So summing up, exceptions can cause very complicated non-local branching in your control flow. When an exception happens, first, the runtime identifies which catch block is going to handle this exception. So it can possibly be running up the call stack looking for exception filters and running them so that it can figure out which call block is actually going to be the one that it transfers control to. Once the runtime has figured out which call block am I going to, then it starts running the finally blocks from inside to outside as control leaves the try block or the catch block appropriately. Operating system resources like streams, readers, writers, all of that stuff, they have to be disposed of when you're done with them, regardless of whether or not an exception occurred. And if you're using the using statement, you can use it as a syntactic sugar for the try finally that you would otherwise have to write to clean up the resource. So I strongly encourage you to use the using statement. It is much, much easier than writing the try finally logic. You can use the static method on file for reading and writing simple, small text files. You can use stream writers and readers for large, complex files.